Welcome, everyone. Today, we are diving into one of the most fascinating survival strategies in the animal kingdom, polymorphism in Cnidaria. If you have ever wondered how simple, brainless organisms can coordinate complex tasks like hunting, defending, and reproducing all at once, you are in the right place. We're going to build our understanding from the ground up, looking at how these creatures literally shapeshift to survive. Let us start by imagining you are trying to run a massive, complex hospital all by yourself. You would have to be the surgeon, the receptionist, the security guard, and the janitor all at once. That would be incredibly exhausting and highly inefficient. To solve this problem, a hospital employs different people who specialize in specific tasks, making the entire system run smoothly. In the animal kingdom, certain fascinating creatures called cnidarians use this exact same strategy of teamwork, but they do it in a mind-blowing way. Instead of hiring different individuals, a single colony of these animals grows different body types, each perfectly shaped to do just one specific job. This is nature's ultimate life hack. Now that we understand the basic idea of division of labor, let us look at the formal biological definition. The word polymorphism comes from two Greek roots, poly meaning many and morph meaning form. So polymorphism is the existence of two or more structurally and functionally different types of individuals within the same organism or colony. We call these individual units zooids. In the phylum Cnidaria, this entire concept is built upon two fundamental body plans. First, we have the polyp, which is typically a tubular, stationary form attached to a surface, primarily responsible for feeding. Second, we have the medusa, a free-swimming, umbrella-shaped form, responsible for sexual reproduction and dispersing the species to new locations. Building on these two basic body plans, let us see how they adapt into highly specialized roles. To survive in a harsh ocean, the colony modifies its polyps and medusae into specific zooids. We have gastrozooids, which are dedicated entirely to feeding and capturing prey. Then we have dactylozooids, which act as the colony's security guards, defending against predators. Finally, we have gonozooids, which are responsible for reproduction. A famous example of this is the Portuguese man-o'-war, which looks like a single jellyfish but is actually a floating colony of these different zooids working together perfectly. Without this division of labor, these slow-moving colonies would easily be outcompeted by faster predators. To really picture how this works, let us examine this diagram of a typical polymorphic colony, similar to Obelia. Notice the central branching stalk anchored to the substrate at the bottom. This stalk connects everyone together. On the left, you can see the gastrozooid, equipped with tentacles to catch food for the entire colony. On the right is the gonozooid, which houses tiny medusa buds, ready to be released for reproduction. And lower down, we have the dactylozooid, positioned to defend the stalk. Every zooid is physically connected, sharing resources and communicating. This diagram beautifully illustrates how different shapes serve different survival functions within a single unified organism. Having seen what these colonies look like, we must ask why nature favors this complex setup. The primary reason is efficiency. By dividing labor, the colony drastically increases its chances of survival in a harsh, competitive ocean environment. If every zooid had to hunt, defend, and reproduce, they would waste enormous amounts of energy. Instead, specialization allows the colony to operate at maximum efficiency. In the real world, Understanding this biological division of labor is incredibly valuable. It helps scientists study evolutionary biology and colonial behavior. It even inspires human engineering, particularly in swarm robotics, where engineers program multiple simple robots to take on different roles to complete a complex task together. This incredible efficiency we just discussed can actually be measured mathematically. To truly understand how a polymorphic colony survives, we look at its energy balance. The formula is e-Net equals NF times EG minus N total times EM. Let us break this down. E-Net is the total net energy available to the colony for growth, measured in joules. The variable NF stands for the number of feeding zooids, while EG is the gross energy gathered by each individual feeder. So the first part is total energy gained. From that, we subtract the total energy spent. The symbol N total is the total number of all zooids, including defenders and reproducers, and EM is the maintenance energy required to keep a single zooid alive. If the number of non-feeding zooids increases too much, the colony burns more energy, and E-Net decreases unless they grow more feeders. Now that we have our formula, let us see this with a concrete example. Imagine a small colony with a total of 50 zooids. Out of these, 20 are feeding zooids. Each feeder captures 15 joules of energy per day, but every single zooid requires 4 joules per day just to survive. We need to find the net energy. First, we calculate the total energy brought in by multiplying the 20 feeders by their 15 joule intake, giving us 300 joules gained. Next, we calculate the energy spent by multiplying the 50 total zooids by the 4 joule maintenance cost, which equals 200 joules spent. Finally, we subtract the 200 joules spent from the 300 joules gained. Our final answer is a net energy of 100 joules per day. Because this is positive, it physically means the colony is thriving and has surplus energy to reproduce. So, we have successfully used the formula to find net energy. This brings us to a more critical survival question. What is the absolute minimum number of feeders a colony needs to not starve? Let us derive this break-even point for a larger, more defensive colony. We are given a total of 200 zooids. The environment is tough, so maintenance cost is now 5 joules per zooid, and each feeder gathers 20 joules. To find the absolute minimum number of feeders, we must set the net energy to exactly 0. This represents the exact point where the colony is neither growing nor starving. We substitute our known values into the energy balance equation, giving us 0 equals the unknown NF times 20 minus 200 times 5. This sets up our mathematical derivation. Continuing from our setup, we now need to isolate our unknown variable, the number of feeders. First, we simplify the right side of the equation by multiplying the 200 total zooids by their 5 joule maintenance cost. This tells us that the entire colony requires 1,000 joules per day just to survive. Our equation becomes 0 equals 20 times NF minus 1,000. Next, we move the 1,000 to the other side of the equation by adding it to both sides. We get 20 times NF equals 1,000. The mathematical reasoning here is beautiful. It clearly shows that the total energy gathered by the feeding zooids on the left must exactly equal the 1,000 joules required by the entire colony on the right. Now for the final step of our derivation. To find the exact number of feeding zooids, we divide the total required energy of 1,000 joules by the 20 joules gathered per feeder. Dividing 1,000 by 20 gives us exactly 50. So the colony must have a minimum of 50 feeding zooids to survive. The intuition behind this result is fascinating. Since 50 is exactly 1/4 of the 200 total zooids, it practically means that exactly 25% of the colony must be dedicated to feeding in order to support the other 75% that are defending and reproducing. If the number of feeders drops below 50, the math tells us the colony will begin to starve and die. We have covered a lot of ground today, so let us summarize the most important ideas. First, polymorphism in Cnidaria is a spectacular evolutionary adaptation where a single colony develops specialized zooids, primarily based on the polyp and medusa forms. Second, we saw how gastrozooids feed, dactylozooids defend, and gonozooids reproduce, creating a highly efficient division of labor. Finally, we proved mathematically that this teamwork is governed by a strict energy balance, where the feeders must gather enough energy to support the entire population. You have now mastered both the biological concepts and the mathematical reality of how these incredible colonies survive. Great job!